Yeah. Thank you, James, for give us this opportunity to just talk us through our work related to applied quantum computing. And since the overview is very preliminary and the basic, so just run us through. And if there's any topic you think it is too simple, we skip over. And if there's anything we want to talk more, we can organize another time. And the currently the project includes we have a I'll say have a very strong team, and we have a very smart young scientist, Christoph, sitting here, and we have world famous scientist Tony Murphy online, and so join us today. Clement is really the top software expert. I'm not sure if Peter is going to join or not. He's a RMT specialist. The only one that's him as a weak point is me. So, but I do have the people. With me, if I make a mistake, or other people will correct me. All right, and so for the basic content, I want to go to the top one, but basically it's cover like some background information, the basic concept of optimization, DCM, that's we use as online example and to demonstrate, and the concept of licensing class and QUBO. This is the basic for formation. Then we narrow down to quantum annealing and also the simulated annealing. And then I get to a very special talk about the quantum computing aeronization. That's our in-house capability. Okay. And I forgot the animation. Anyway, so just as a big picture, the landscape, uh, this is related to the quantum technology, and just for today, it's related to the quantum computing. But quantum technology really include the quantum sensing, quantum communication. That's most people are talking. But really, there's a much broader scope, and I particularly put down quantum battery. I guess you know the term, right? So I think it really is anything you use quantum phenomena. That's a quantum technology, and the quantum battery. We know that how important is battery, right? And if you're talking to battery for so many years, it's all electrochemistry. Really, that's not should not be the case, and I said like a quantum battery and some talking about a nuclear battery and all that. So we really need to break out the box. So we are so fortunate CSO has a vision to include quantum battery and also we also like to get the visionary scientist James. So that's really I see this a very important direction. Of course, we are not expecting next year we'll get a quantum battery, but in the future. Then we talk about quantum, computing. Really, when I'm talking to most of people say, okay, quantum computing is gate model quantum computing. That's IBM, the Google and stuff. It's more generic quantum computing. But for instance, we are focused more on the quantum annealing. And you might hear some people say, all right, quantum annealing is not quantum computing. But I want to argue is because it is still using quantum qubit to do computation. It's not a classical computer. I don't know if it's a quantum computer or not. I'll leave it to other people to decide that. And in quantum annealing, there's two aspects. One is the application aspect. Just use quantum annealing to solve problems. Another is for developing the quantum annealing system, operating system, all that. That's basic. So we focus on what's application. In application, the main the area is related to combinatorial optimization, basically the discrete values, and the material modeling is specifically, and logistics, scheduling, and process optimization, etc. And For our research, the main focus is the three dot points. One is the improving the computation efficiency. The second is to solve large problems. This the economy is still small, so we may need hardware computing. And also that's all guided underlying these high impact applications. So, okay. Now just to get the basic concept of the optimization. I don't know if everyone's familiar with optimization or not. Just use as this is a baby problem. The problem here, the description is we have four people, X, Y, W, and Z. And we have two rooms. And X, Y is friends. Y, W, they are enemies. And W, they are friends. So we want the friends to stay in the same room and enemies not in the same room. So that's the objective. And then now we introduce numerical notation. If we say X equals 0, that means person X stay in room 0. If X equals 1, that means person X stay in room 1, etc. Okay, now this is a problem. The mathematical formulation is okay. First, we need to write down what's the constraints. So for X and Y, and we write down as X plus Y minus 2X. Why we write this way? It can be other form, but this is one way to say that. Is if X and Y both are 0 or 1, this gives a 0 value. And if X and Y is a different value, one is 0, this gives 1 value. So basically, if they're in the same room, have a lower value, a different room have a higher value. So that's a principle you got it down. And the others are saying, but if the enemies, you just put a negative. So basically, -1 is lower than 0. Then if you think all the constants are equally important, so just add them together, that form called objective function. And this at this point, it's become unconstant objective function. The constraint is already part of it. So that's the final the mathematical expression here. Then to solve this problem is it's just adjusting at the these variables X, Y, Z, and W to derive the smallest value for the objective function. That gives the solution. And this one here is actually that is solved by the derivative on the left. But for this problem, really, you don't need any computer or quantum computer. So you can see that in a different XY values, and it have a different objective function value. And the lowest value is -3, with XY 0 and W and Y 1. So that means either X, person X, and Y in room 0, and then W in room 1. That's one good solution, or the best solution. And there's also another one here, the other way. So X and Y in room 1 and the Z and W in room 0. So they are equally good solutions. And so now the in this form, that's one of the fundamental common, the standard form. It is called the Kubo form. That's a quadratic unconstant binary optimization. And also, that's for optimization problems typically like that way. But if you're modeling any of the physical problem, quite often use the spin notation. So that's using Ising spin notation as -1 format. So spin up, spin down notation. That equivalent. So and if you get to more general, then a different constraint might have a different penalty factor, different importance. So mathematicians call them Lagrange multiplier, and the optimization person calls them penalty factors. And also you can add others to say that each room must have 2 people, or each room can have up to 2 people, etc. And so this is a special form of combinatorial optimization. All right. I don't know if any questions. Or feel free to interrupt, particularly if I make a mistake and I'm misleading. So now let's get to slightly more the realistic and complicated. This is called DCM, and it's a data constraint model. So this the name created from my first paper in 2007. So it's nearly 20 years. And this is for determine the three-dimensional material distribution, macroscopic material distribution, using Amelia's actually CT data and using the principle of statistical physics. So the formulation is actually, you can think of optimization problem. So basically, the material is represented by cubic lattice. Okay, on each voxel, and try to you can have multiple materials. Like we here is the volume fraction of each material, and so they are non-negative and less than one, and added to one. So this is the strict constraint for each voxel. And in each voxel, you also have actually measurement. That's a linear attenuation coefficient, and that's related to the material. So the difference of the calculated and the measured actual absorption will be the same theoretically, and realistically they have differences, but need to minimize this difference. And so on each voxel you have say 3 materials, 2 actually, so you get 3 constant here, 4, and 2 actually. That's 6 constant. And the typical problem size is like 1,000 cubes, so about 1 billion. So that's multi-billion constraints. And for a more industrial related or the more realistic problem, you can have to can easily get to 500 billion constraints. All this added together, and this also the interaction and so this in optimization sense, this optimization problem. Okay. And of course, if you do a Google search data constraint modeling, in the past, when this is active research, and we are 90% is us, now it's about 50%. So other people are taking over it. But still, got most far now. All right, and the for a more simplified version of it, if for the binary version of it, and this can be easily formulated as the Ising format. So you get a quadratic term here and a linear term here. You get this is a field and this is the interaction. So S here is a spin. Okay. So we'll use this as an underlined case to test for the quantum linear. Oh, this one. Maybe I'll skip over this one. This is a little bit of philosophical. We'll skip that. Oh, we check the time. Yeah, okay. The time is all right. Now when try to solve this type of problem, there are 2 types of the commonly used computing platform. The first of the general concept called the classical computing and the quantum computing. Basically, a computer is just a program machine to implement some mathematical like logic or something like for classical computer, they typically use electric current voltage as a physical quantity. But you see a lot of people, if it's particularly YouTube, that people use fluid, water, to implement the Boolean algebra gate. And I think this all, I think in the very early days, built a fluid computer. I think 23 know that a lot. I saw that just using water pipe to implement some of the computer. And those physical quantities, if you're familiar with the quantum mechanics, that's called observables. And use this to form representing binary 0 and 1. And each one of them, they are discrete value binary and independent. They're independent values. And today's computer you have billions or trillions of logical qubits. And the error rate is kind of very low. That's 10 to minus 18. So you can virtually treat them as error-free. And the subtle difference, the quantum computers, it is a processor to process wave functions rather than physical quantities or the observables. And of course, we need to get to the observables. That's only at the end you collapse it, become the classical quantity to measure. Common implementation like the superconducting current. That's one common, like the DV1 as a superconductor. And then also if people use photons or use particle spins and anything with the quantum quantity. And the subtle difference, why is it different is because quantum wave functions have property of superposition and entanglement. So this is a sense that a classical computer don't have, and there's no classical analogy. And why it is important, the superposition allow one processor to process a superposition state. That means you can have virtually an infinite parallel processor. Classical computer, you only have one thread plus another thread. But in quantum computer, in principle, you have infinite. And also the entanglement is also an interesting one. So it's the qubits are not independent, so you have can use a spatial correlation or coherence. The problem is the quantum computer nowadays is because the number of qubits is very small. With gate model computing, tens of 100 maybe, and with the quantum annealing, it'll get to thousands, like or simulators can hundreds of thousands. So the that's still quite small. And one of the important killer factors is the error rate, very high. Point something up to 1%. Okay. So why? Okay. Now the what is how people use it? How they use it? This the quantum annealer for typically you formulate the problem or computing problem or optimization problem as computing the ground state of Hamiltonian. And is specifically formulated as Eisenstein glass or Kubo format. And then I perform multiple computations. From here, there's also the become kind of different from the conventional computing. Generally, we think that a computer is repeatable. You just do the job, get the answer. Do the second time, get the same answer. But then generally for the optimization, the computation is not the case because it has a different probability to converge to the different the minimum or local minimum. So typically you start with the independent or randomized initial conditions. So it has a probability to fall, converge to the different minimum, and has a final chance to get to the global minimum. That's a tool of which we want to use. In today's up to today, the computing platform is like the Python language, and the computer access is typically through cloud because it's rapidly changing, and also this is like the DRAM machine is at $10 million per unit. So if you buy it and 2 years later, it's become too old and obsolete. So it's best to use a cloud access for the QB. As I mentioned earlier, the formulation is always you get the prompt to formulate into a async format. In terms of principle, for the similar annealing is basically thermodynamics. Maximize entropy and minimize energy, or in a balanced way to minimize free energy. So what you do is, okay, you start with a high temperature, infinite temperature, so everything is random, is gradually lower temperature, you annealed to the ground state. And so this is all implemented using classical gate, and a typical time it will computation in 10 seconds. It can be faster, it can be slower. Some of them maybe a millisecond, but some can be minute. So there's various different implications, and Japanese actually dominate this. I don't know why. So there's a number of machines. So one is like we access the NEC machine that has 100,000 qubits, and the quantum annealer is based on a different principle. It's called adiabatic theorem. So basically, in a simple the understanding and relate to the quantum annealing is okay. If you have a Hamiltonian at zero, you know, relatively simple, you know what the ground state. Okay, then you gradually change it adiabatically, so there's no external temperature or energy flow in. If it changes Hamiltonian, the system is still stay in a ground state. And so in a computationally, basically, you just switch t from 0 to 1. So that become the different Hamiltonian, but still stay in the ground state. And earlier we said you get the optimization problem as computing the ground state. So theoretically, this will converge. Okay. And this is the for implementation is always implemented QIN. And the typical time to do a computation is about 0.1 millisecond. Can be longer, can be shorter. And but this is related to the more related to the coherence time. So you can achieve that. Of course, you can have different qubit implementation. The DRAM system is a superconductor. So the current commercial system is have 5,760 qubit, and the near machine is supposed to be 7,000 at the current moment is 1,200. For the user difference is really the similar annealing is local minimum limited. Really, the enemy is local minimum. And for quantum annealing, the is noise limited. So noise is the top killer that prevent a conversion. Okay. I'm going too slow. You wanna?
You went a little bit faster, yes.
All right. Okay. Then it just very quickly. So the what is the qubit noise the impact? Basically, the principle is that if you solve a problem, you need every qubit to operate all correctly. But if with a large number of qubits, the probability to get every qubit work correctly is small, right? So you can see it here. With 100 qubits, the chance you get answers all good. But if you get to large numbers, say 10,000 qubits, and the quantum computer have to never get that answer. All right. And the local minimum is also another factor to affect it. And I don't think that the current thinking of 1,000 people could get one corrected or corrected qubit. It might not be realistic. Okay. Now just get to our the in-house you mentioned to addressing this qubit noise problem. Okay. The underlying thinking is this. Okay. The one thinking is all right. We try to fix all the noise, but I think that's difficult. So what we do is here is okay. We don't fix it the qubit noise, but even if we have an answer that is not perfect, have some errors, but it has a large amount of useful information. So I just use a car analogy here. You got a punctured tire. It's not a road race car, but it's repairable. So we use that. Basically, we use is a repair the non-perfect answer to get it to better. And this has been patented and has the implemented as software, and we can use. Okay, now let's get to the point. How does it perform? So we use the underlying case as the DCM as underlying case with different sizes of the cube, and so the smallest is the 1 cube, and then gradually 2 cubes, 3 cubes, etc. Get to 8 cubes. You can see the black curve is the result similar use and just the D-wave the machine, and you can say the start from 0.1 millisecond to about over 100 seconds. So when it gets the problem gets size getting large, there's got a million times more. Then we have 2 different implementation of the you mentioned as symbol, and you can have one. One is but still maintain about 0.1 millisecond. So at this point, it has a million times better in convergence. So that'll make it easy, make it more practical to solve real problems. Okay, well, just slow down here. Is there any questions so far?
Yeah, I have a few questions. I think you got one slide there, so I'll just ask them now. Okay, so this CMO algorithm protocol. So it's software, right? It's not hardware. You don't actually physically reduce the error in the spin qubits of the system. You put in some algorithm that somehow effectively reduces the error. Is that am I right thinking that?
I'm gonna say it's post-processing.
It's post-processing, yeah.
Yeah.
Because if you give no detail about the algorithms, I was sort of asked what from the slide. So the spin error mitigation is only for optimization problems.
Correct.
You can't use it generally.
Correct.
I know this proprietary software, but can you talk a little bit more about CMO details, or you can't do that?
I think at this point of time, I try to not to say too much details. Just how you use it, but not about how to operate.
Okay.
That's how we're.
I get that. Because I mean that part is the most interesting part, and that part is the big black box at the moment.
Yeah.
Okay.
So you can think of it as a black box. When you get a computing result from the quantum computer, pass the black box, and come out with a better answer.
Yeah. Yeah. So, but the problem is, like, if I have a problem, I can't just use this. It has to be a very specific type of problem that you can apply CMO to.
Yeah. Right. Okay. This is a good one. The quantum computer or quantum annealer, basically you need to formulate the problem as either QUBO or Ising format.
Right. Yes.
So you need to get to that point.
Yes.
And CMO take the Ising or QUBO format and come out with that.
Yeah, but I think you're saying that it's only valid for like optimization and minimization.
Optimization. That's right. Yeah. That's right.
But okay. So is it valid in general for all minimum type problems or minimization type problems? Or is it very specific?
All right. Okay. To use the quantum annealer.
I'm talking about for CMO.
Yeah, you need to formulate into the Ising or QUBO format.
Yeah.
So you need to the CMO work for the Ising or QUBO format.
Yeah. So yeah, so if I can formulate it into an Ising model, CMO will work.
Yeah, that's right.
Right. Okay. I'll have one more question though. I can answer before. So the vertical axis there. How did you? Well, what's the vertical axis?
That's a time in a millisecond. So you can say that the for the small problem, it's 1 millisecond to get answer.
Yeah, the thing I'm not getting together is CMO is an error mitigation algorithm.
Yep.
How does that, because it's a black box, we don't understand how this works. How does that reduces the computation time?
Oh, right. Okay. So that's very, I didn't explain. So the, to get the right answer, you need to do the combination many times and find what is the lowest. The lowest repeated, and you think, okay, this is the ground state. So the time is calculated by number of repetition.
Right. Yeah.
So if you without using CMO, typically you need multiple million times of repetition computation to get the say you do.
I think it's more of a number of shorts problem, like, yes.
Yeah,
Yeah.
yes. So that's what I suspect it was. Yeah. Because, yeah.
But if you use a CMO, it is actually get the about 88% of the time you get the right answer. So you don't nearly need that many repetition.
Yeah.
But without it is for the 500 variables, repetition rate is like 1,000,000 times you get the one right answer, an average. So to get the confidence, you may need 100 million times computation. Right.
Yeah, I mean, any other point, comment?
So I've got a few questions. So in particular, Sam, when you're talking about the quantum annealing, the kind of idea behind it is to take a non-interacting Hamiltonian, adiabatically evolve that to the interacting Hamiltonian, and via the adiabatic theorem, as you say, you go over to the interacting ground state just for free, essentially. But this is providing that your time parameter is slow enough. So to have the adiabatic theorem to hold,
Yep.
you need to have a slow enough time, which is slower than at least the first energy gap, right?
Right.
So first of all, how can you guarantee that? And second of all, what happens if you have a degenerate ground state, for instance?
Oh, okay, right. That's a two points. There's no guarantee. That is so it has reasonably high chance to get to excited state rather than ground state.
Okay.
And so okay, this is also become the problem selective. Some problems, if you kind of formulate the problem, the ground state, then the first excited state has reasonably large gap, then that's a good problem.
Yeah.
So the so quantum computing is not OQ. It is just for some problems may work better, but not for all.
Yeah.
And the degeneracy, the ground state, that's very common. Very common. So even if have the same energy, the spin state may not be the same.
Yeah.
But in terms of the solution, they should be all equally good solutions.
So I know in general when you adiabatically evolve degenerate manifolds, you can have the accumulation of non-abelian geometric phases.
Sorry.
So your wave function can acquire a geometric phase, which is non-abelian. It's not just a simple phase, but it actually mixes together different states in the degenerate subspace.
Right.
So if we go back to your XY and WZ problem of having people in rooms, so there are degenerate solutions there where XY can be in room 0, and vice versa.
Right.
You could end up in a situation where you have a linear superposition of these two. Situations, right? You know which one to pick.
That's a very good point, and I don't know everyone understand it. Yes, when you get it, you may have a solution. XY, room 1, and also XY in the room 2, but it's not just one or the other is a mixed state, and hopefully by collapse to the solution, it will collapse to one, and that's still a good solution.
Okay. Okay. Yeah. Yeah. I mean, probably
The,
because if you have a linear combination of
Yep.
eigenstates which have the same energy,
Yep,
then it's just as good an answer as a
Yep.
linear combination.
yep.
Okay.
So at the last, that it may not be a purely one solution.
Mhm.
It can be a big mixed good solutions, but to collapse to any one of them is still a good solution.
Gotcha. Okay.
I don't know.
Yeah. No.
This is just a big assumption, and it's not a.
Okay.
This is actually the big assumption, really.
And then, so if I may, just one more question.
Yeah.
So the form of this, the T, so the Hamiltonian basically that you write on this slide. So I realize that with the current technology and things, you need to formulate your problem into an Ising sort of Hamiltonian basically.
Mhm.
Is there any gain or any benefit of doing quantum annealing with an extra terms, say in your Hamiltonian? So if you have a Zhelezhinsky-Moira interaction or some zero field splitting of your qubits or something like that, just is
Yeah,
there any?
yeah, that's actually, I think that for future annealer, maybe, the idea that theorem doesn't need to be the Kubo or Ising.
Yeah.
So, but the current design is that way.
Mhm.
That's the current machine is designed that
Yeah.
way. So it's not
But
necessarily,
is there, can you foresee any enhancement of like, so any different problems which could be addressed with this extra little bit of physics in the Hamiltonian as opposed to what is state of the art now?
possible. The topic is in this the current the space. There's only one commercial machine of the OEM. So
Okay.
that design that way, but it not necessarily have to be that way.
Yeah.
So the future machine might be different.
Okay.
And AC is going to release a machine, let's say the 2030, and will be different.
Cool.
So
Thank you.
So the only sentence, if you use a machine today, yes, they are Ising and Kubo.
Mhm.
That's the
If I have a problem which is represented as 512 spins, can I still use CMO with 512 spins, or do I need more qubits to implement CMO?
no. The it use exactly the same for the because it's post processing. So the same runs on the local machine.
So CMO is classical computation.
Yeah.
Oh, I see.
And very efficient.
Right.
So this doesn't complicate the quantum aspect.
Right. Okay. So can I almost say that this graph here is a little bit cheating in the sense that it doesn't include the post processing.
Doesn't include post processing.
And but your argument is that the post processing is insignificant.
Yes, very little. And of course, it depends on how much. If it's a lower curve, if it's an upper curve, this is a very efficient implementation. For this particular problem, it'll take out of 10 milliseconds.
Mm.
So you can imagine even at or 10 milliseconds to process in like 3,000 results from.
And does that post processing scale linearly?
Linearly.
Linearly.
Yeah, that's it.
Right.
Yeah,
Okay.
yeah.
Okay, so that should be okay. So that look okay. So green there for some reason is just flat. I don't. Okay,
Oh,
okay.
okay.
No. It's linear. Just it's very.
Yeah, so very linear. So you
That
cannot
that's
say-
both linear. Classical is linear, but your argument is that with that CMO, it's non-linear. So for large N, you will win. You will win not like exponentially, essentially.
That's right. Yeah.
Okay.
So the classical process time is linear.
Mm.
So if we include that, and also there's another sentence cheating there also. And when I plot the quantum computing time is only the for the read time. Basically, when you do a quantum computing, there's time you need to embed the problem to the quantum computer. So there will be input output. So first you need to set up the coupling and the qubit state.
Mhm.
That is proportional to the problem size. So there is also a linear component there.
So say that again.
When you set up the quantum computer, like
Yep.
if you set up one spin to do the job, or set up 1,000 spin to do the job, the setup time for the quantum computer is different. So basically that's the input output time.
Yeah.
And also another time is not included here is when you do a computing, you don't do immediately another one. So there is a gap, time gap. Just get the quantum computer to settle down, to forget about the past, basically.
Yeah.
So, but that's again,
Yeah. The non-linearity of the of CMO makes sense because you're post-processing essentially each run. And
Yep.
so therefore you don't have to worry about, there's so many, it's just each run you post-process, and so you don't have to expand the Hilbert space because each run is separate.
Each
So
one is
that's
separate, yeah,
why
yeah.
it's why it's linear.
Each one is separate,
Yeah, okay. All right. Okay. Yeah. Okay. Yeah.
So for similar,
Yes.
basically all I can say is that you only have gain and there's no loss, basically, apart from extra the local time.
Yes. So D-Wave don't have, like, not necessarily CMO, but wouldn't they do some sort of do this anyway, like for each run, to account for errors?
All right, okay. The DWave will offer two. One is a direct on the QPU. They did direct annealer. Another one is they're pushing more for commercial users. They're called hybrid computing. So the that is have heavy classical computing, very little quantum, and but not in the same way as we do.
Right.
And
But does D-Wave, actually, I don't know the answer to this, but do D-Wave have post-processing to mitigate errors currently, or no?
as far as I know, no.
Okay. Okay.
But they have two different classes of offer. One is a direct the QPU access.
Yeah.
Another one is a more solution oriented.
Yeah.
It's called the hybrid solution.
Yeah.
And they essentially so
Yeah.
for us to feel that's just a classical solver basically.
Yeah. Yes. I mean, this is a good gap if D-Wave doesn't do it. Have you spoken to D-Wave about this? Are they interested?
They said they're gonna get back to us
Okay.
and follow up it.
Yeah.
In the last, have you been at in last the Quantum Australian conference?
I went for the first day. I didn't go for
Oh, the first day, yes. D-Wave actually sent 2 person over.
Yeah.
And but the D-Wave is that they nowadays used to be a very much government supported R&D type of company. Now they want to make money.
Bastards.
So they said, "Oh, we don't have much research in the anymore, so we just basically want money."
Yeah. But this is a very good selling point, like
Yeah.
to someone like D-Wave,
The
right?
deal with that, they also talked to AC that seems to be more interested. So AC is more the classical delay.
Yeah.
But still, still trying to talk to them.
Yeah. I
And
mean,
yeah, we saw that if you have like a post-processing software, that may or may not be the best solution. I saw that if it's become an error mitigation chipset to build on the chain, there's no point you pass user the result to contain error, right?
Yeah.
So little user. Oh, I want to say it's no user, but a little user. The people they use the result have error, so to simulate some of the final temperature.
yeah.
So
Yeah. And this is the sense is a very simple solution, but it's a very practical solution,
yeah,
and
yeah.
it's in a sense very effective as well. So
Yeah.
Yeah.
So far it looks like it's very effective, and the overall time it is much shorter.
Yeah. It's, yeah, good gap to fill.
So I thought if you can find some problems and may take advantage of.
Yeah. So, but our work in this in the quantum space is we've been working in the few qubit space, mainly because going to high number of qubits is not really practical at the moment. So we really don't work.
That's a gate model. That's a gate model.
Yeah, you take model computing. Yeah, we actually don't do any annealing type problems yet, but you never know. We're looking at optimization problems for quantum battery materials, which maybe some of this could be useful, but yeah. We're not
This
doing
is
that right now.
their application is narrowed down to optimization application rather than more generic.
Yeah. That's right. Yeah. Okay. I think you want to conclude with one of your last slide. I think you have one more slide.
Yeah, this is just like a summary of what we said. I think we have basically the annealing is for solving optimization problems, and the current fundamental format is ISIS because qubits, as you said, this is the current offer. It's not necessarily a limitation. And to construct the problem is basically just a weighted sum of constraints.
Do you think your one would be useful in like in a like standard quantum computer, like the gate-based one?
Yes, that's we haven't started talking, but I started talking, but haven't tested. You know, the optimization, is optimization is also one of the problems to solve. And so far, you know, Rigetti, they have a team working. So we're going
Is CMO generalizable to general problems, to general spin mitigation, or it's very specific to optimization?
Perhaps not.
Okay.
No, we still don't know an easy pathway to do that. Because there's a post-processing. So if because the annealing, they have that general format, I say no cubo. So we solve that. If we solve a different problem, it is it'll be a different problem, you know what I mean? So different problem, so you may not
You include like some pre-processing and post-processing, then maybe.
sorry.
I mean, if you have some pre-processing and then you go with quantum system and then you have some post-processing, do you think you can have some gate model for CMO as well? With some pre-processing as well.
Okay. Pre-processing is an interesting point. For optimization, for more general case, you don't want to do pre-processing or set an initial condition. Because if you think it come with answer, high probability is actually close to 13 local minimum, not global, right? If you try to use that as you think it as a good guess or a good solution, it might be misleading. I don't know if you know what I mean. So for general cases, you don't want to impose an initial condition, so that give the pre-processing. If you think that that's a pre-processing, but if you kind of formulate the problem to be more efficient for quantum annealing, and then that will be a good thing for pre-processing. But if you think there's a set of initial condition, that is as a case by case, may not be a general.
Yeah, I wonder. I mean, I don't know, but from the field, but like generally in quantum computing, there's two approaches to noise. One is to make the qubits higher fidelity, and two is the general one where you just create more qubits to encode the error. But your idea of post-processing classically, I don't know how much of that's been done in like in gate-based quantum computing. It might be a sort of a virgin area to investigate.
I'm not sure. We did the Tony was out of the book. Initially, we searched a large number of or screened a large number of patents.
Mm.
And it started with sort of 400 and narrowed down to 100, and still trying to find any in this.
Yeah, I imagine there is, but that's just that your work sort of shows that it could be quite effective, and it might be motivation to really drive this alternative approach.
Yeah, but you need to narrow it down to a class of problem, because the post-processing is quite often is problem dependent.
Yeah, because I don't know what your algorithm is, but the ultimate would be have a general one. You'd use it for any problem, right?
Because the post-processing, you still need to know the problem. Like this is the ISIS problem, there's a Kubo problem. You know what I mean?
Yeah.
Okay. If it's a general problem, then you need a general class of problem in that format.
No.
You know what I mean? So
I do. Yeah. And if you find this general one, you win the Nobel Prize. Especially if it's effective.
It need to be general enough.
Yeah.
So that's the reason we selected optimization, because they all formulated in the Eisen-Kubo format.
So, like right now, you showed that you with CMO you have to reduce the time. It reduced the time of implementation as compared to quantum annealing from D-Wave. So, did you compare your results with like just simply classical solution and using the quantum with CMO? So, how does it compare in terms of time implementation?
So sorry, you mean use on classical solver?
Yeah, only like purely classical.
Okay.
Optimizer to solve the same problem, and then the same thing with
that's also very tricky. I think that generally, if you have a good quantum solver, and generally you'll find a better classical solver.
You find a better classical solution.
Yeah, they still what I don't think that anyone still have a problem that the quantum is.
I'm saying like just in terms of the implementation time, not in terms of quality of the solution.
Even implementation time or runtime?
Runtime, like the whole complete time, like for the
execution time, like the
execution.
Yeah. I think they still not a. Do you know that recent the New Scientist article that Google that put down $5 million?
Yes, I know that.
You know that. So that's an indication. We're still gonna have the quantum computer have it.
My point here is like after quantum, you are doing some post-processing by using CMO.
Yeah.
So normally, like even in the theory, the quantum advantage in terms of implementation time that we claim. So do you think like it will be affected by, even if let's say we have perfect quantum computer and we can do some good computation on that very fast as compared to classical, but then we need some classical post-processing. So does it going to affect that claim that we have in terms of quantum speed? Because normally in quantum error correction and quantum error mitigation, normally people use classical machine learning. And then I do have this kind of question like in mind, like how then we're going to have that quantum speed up if the quantum is being controlled by classical?
You mean if added quantum and the post-processing
yeah, I mean like even after the implementation, we have some post-processing to mitigate that errors. So do you think we still, even in the theory, do we still have that kind of quantum speed up that we claim in the theory?
I understand his question because I sort of think the same thing. So if your significant improvement is because of a classical calculation, your CMO, and then you tell us that CMO is specific to this optimization problem, and the question is what's left, like in the quantum part of it, is there any advantage? Like if you have a significant improvement due to the classical CMO, then a good thing Carl was suggesting is you need to compare it to a classical algorithm, because so much of the advantage seems to come from the classical CMO optimization, right?
Oh, right. Yeah, that's a good point. I think for just as related to DCM, the currently we can see if it's with vanilla plus Simo, it is kind of a comparable classical implementation.
Like if you look at, for example, Shaw's algorithm,
Yeah.
90% is classical, right? But there's only one bit which is quantum, and that one bit makes it exponentially faster. In this case, it's probably I don't know. I don't know if that quantum bit is that powerful or not, right?
Yes, okay. Now I know what it means. So, all right. This is a good point. And because the why the optimization as a computation is inefficient? Because one is a noise, another is related to local minimum. If you just imagine how complex the energy landscape go up and down, there is one place which is really deep, very narrow. And if you use another classical simulator, you may have a very small chance to get to the
that's true. Like if you assume the Nila is perfect and the classical algorithm is fine, then Nila will win because of this. But what you showed is that if you have a classical algorithm which is CMO, which is specific to this optimization problem, you can have a drastic improvement.
Yeah.
And so because we don't know what the algorithm is, and so it sort of leads to the question.
Since if there's no noise for quantum vanilla, still, let's guess, potentially that has a better chance to converge to very narrow minimum. So from there, you may demonstrate some the quantum advantage. If that's the case, this is purely a case scenario, because the adiabatic theorem says it'll get to it, right? But does that perform any better than the thermodynamics or not? We still don't know. If there's a formula to that, then you may that demonstrate the quantum advantage, because with SIMO, the noise factor is essentially eliminated.
Yeah, but with the classical algorithm.
Yeah, but since if this is no maybe the Christian Tani, you may want to comment. Since we don't know if there's no noise, would adiabatic quantum computing outperform the thermodynamics or not? All right. If yes, then this may potentially demonstrate advantage, but we don't know.
Yes, that's right. That's exactly it. Yeah. Because you can't. Yeah, exactly. We can't. Yeah, exactly. Yeah.
But
you can't. Yeah.
For I'm saying it for some problems.
Yeah.
It may have advantage. That's where we may aim it.
The converse of that is that because your algorithm works so well, it may lend to the notion that the quantum vanilla, in principle, cannot work better than classical, just because your classical works so well, right?
Okay. So there you go. But the symbol is only just addressing the noise issue. Still, the advantage delivered is through the adiabatic theorem.
Yeah, I'm only speculating because I actually don't know what your algorithm is. So,
Right.
yeah.
In 1D, you can go away without the quantum adiabatic theorem and just write down the essentially path integrals and the Metropolis Hastings updating rule that you have in simulated annealing. And then you'll see two things that you have: the height of the energy barrier between the local minima and a global minima. It's the 2 points that you're essentially trying to connect. And you'll see that quantum tunneling is quadratically more efficient than Metropolis Hastings updating rule with similar with a similarity with time and temperature being equivalent in this, being compared in these approaches. How it works in a very complex scenario with a very complex multidimensional work is an interesting research question, I guess.
Oh, okay.
To set up like the family of Landau-Zener theorems in a very complex manifolds.
If you can formulate the problem, that's kind of relate to reality, realistic problem to demonstrate that. That'll be even theoretically, even it's not numerically, that'll be I think it'll be is a candidate to claim that formula.
Google is smart.
Okay. Well, yeah. For time, we got the time. So let us take Sam again. Yes. Okay. Thank you. I'll end the recording.